Higher Notes, Unit 1, Section 5, Gravitation. This is part 2, where we'll look at projectiles and satellite motion. Let's just recap a little bit on what we mean by free fall. So a body in free fall is one that's dropped under gravity and falls. So there we are. There's the body. And if it's in free fall, then it accelerates downwards at g for the given planet, which if it's Earth will be minus 9.8 meters seconds to the minus 2. There are no other forces on it other than gravity. Now in real life, of course, there will be air resistance. There'll be a little bit of drag, and as the speed builds up, of course, the drag does become greater. So if this is the situation diagram, the free body diagram for the falling body will look like this. Free body diagram, remember, shows all the forces acting on the body, but only the forces acting on the body, not the forces exerted by the body. Well, obviously weight is acting downwards. And remember that in SQA exams and tests you need to write the name of the force, the full name. You can write the equation in brackets if you wish, and if you know the numerical value of the force, you can always put that in. I'm going to put in drag there, or air resistance. Now the size of that air resistance, of course, depends on the speed. The faster the body goes, the bigger the air resistance. And of course, the largest magnitude the air resistance can ever have is to equal the weight, at which point you have reached terminal velocity. So if we ignore air resistance, then a body in free fall only has the weight force acting on it. That's the gravitational pull of the Earth on that body, and it will accelerate downwards at 9.8 meters seconds to the minus 2. Notice that a body which is in free fall downwards has no horizontal velocity. It's not moving to the left, it's not moving to the right, it's simply falling downwards. Now this is important for understanding projectiles and therefore satellite, because a projectile has two components of motion, and the vertical component of motion of the projectile is identical to the vertical component of motion of a free-falling body. The only difference between the freely falling body and the projectile is that the projectile has this additional horizontal component of velocity, which is a constant velocity. So let's look at that now in the context of what's called Newton's Canon. Newton was very aware of cannonballs being fired and their trajectories through the air, but he was also aware of the moon going around the Earth, and he suspected that the moon was in fact just like the cannonball in many ways. It was a kind of projectile. A projectile following a parabolic path which never actually landed on the Earth. So how can that be? Well, here is Newton's thought experiment. So we imagine the Earth, and on the Earth, in his thought experiment, there was a tall mountain, very, very tall, so tall that it was above the atmosphere. And at the top of that mountain, he imagined a cannon, which fired a cannonball. Now, he imagined then that the cannonball was launched parallel to the Earth's surface, so horizontal if you like. And he imagined that if it came out quite slowly, it would follow a path something like that. Parabolic path. Fairly slow. So the time of flight, remember, is determined entirely by the height of the mountain. And basically, if it's not fired very quickly, during that time of flight, because it's travelling quite slowly, it doesn't travel very far around the Earth. Then he imagined that he could fire the cannonball a bit faster. Now the time of flight is exactly the same as before, because that's only determined by the height of release. But because the second projectile is coming out faster, it travels further horizontally in the same time. So it's gone further round the Earth. Notice in both of those projectiles that the Earth is curving away from the projectile, so they travel a bit further than they would had they been on flat ground. Now what Newton then deduced and reasoned was that if the cannonball came out at just the right speed, then it would follow a parabolic trajectory, which was in fact a circle. And that circle would have a curvature which matched the curvature of the Earth, and that therefore the projectile would go in a circle as shown, and it would come right back round, essentially to hit the back of the cannon, like so. And in fact what is produced here then, it is a projectile, it is a parabola. Remember, a circle is a specific case of a parabola, a special case of a parabola. And he's got the circular motion, and he's essentially created a satellite orbit. Because we're above the atmosphere on this high mountain, what we'll call the horizontal velocity, that's the velocity component parallel to the Earth's surface, is constant. There is no drag to slow it down. So once it's in orbit, it just keeps going and going and going. Out of interest, had the projectile been fired too fast, if you like, to get into that circular orbit, then what it would do is it would do something like this, and it wouldn't land, and it wouldn't go into orbit. It would actually leave the Earth's vicinity and go off somewhere else. So that would be very too fast, if you like. Whereas the green one is the optimum launch speed, and the yellow and blue are too slow. And essentially then, when artificial satellites are launched, they're taken up by a rocket, and the rocket is given a trajectory which takes it into orbit round the Earth, and the satellite is released in that orbit and it remains there. And that's a simplification, but pretty much what happens. So that is how we can understand projectiles. So remember that everything you have learned about projectiles generally, the uniform acceleration under gravity vertically downwards, the constant horizontal velocity in the horizontal direction, all of that still applies to satellites. It's just that the curvature of their parabolic path matches the curvature of the Earth. So a satellite is indeed falling. It is falling to Earth at g, just the same as a freely falling body is falling. One way perhaps to think about it is that every time it falls down a meter, the Earth also curves away by a meter, and therefore it remains at the same height above the Earth. That's one way of perhaps getting it in your head. Okay, that brings us to the end of this note on projectiles and satellites.